In this video, a short overview about the modeling techniques used in the Transcend projects is given. Subsequently, the main Transcend modeling techniques used are classified. These are discussed in some detail and illustrated by 3 case studies which exemplify work done in Transcend. We try to give an overview about the modeling techniques used by the different Transcend projects. There are many ways to classify models. One can classify as numerical and non-numerical and many other ways. In this video, we only look at the numerical models. These are classified according to the length scale on which they work. Models, however, exist on all length scales. From models for the interactions between a few atoms up to models for whole civil engineering structures. The first technique discussed in greater detail in this video is molecular dynamics, or MD. MD can handle volumes of the order of nanoliters and timescales in the order of nanoseconds. Thus, it is well suited to study what happens in a single cement pore. However, as we will see later, molecular dynamics requires information about the interactions between the atoms. DFT, density functional theory modeling, can obtain this information. DFT uses quantum mechanics to model interatomic interactions, such as chemical bonds, in great detail. The author of this video decided that this technique is too heavy for this video, so you have got a reprieve. Since DFT is computationally expensive, little can be done which goes beyond modeling of a single molecule with a handful of atoms. However, DFT data can be used to obtain the interatomic potentials needed for MD. This is an example for reducing the complexity during modeling. Monte Carlo techniques are a diverse field of different techniques which work on many length scales. They are often computationally cheap. The basic idea is that reality is approximated by a suitable stochastic model. The idea will be illustrated by a case study in which MD and MC were combined in a Transcend partner project to extend the timescale of MD simulations. A Monte Carlo technique was also used by Project 2 to build sheet structures for CSH, but this is a topic of a separate video which can be found on the Nanocem webpage. If the length scale becomes large, modeling no longer focuses on atoms as discrete entities. Instead, matter is seen as continuous phases which are defined by bulk properties. In the continuum length scale, there are essentially just 2 methods we would like to mention. First, continuum models. These models are often called finite element, finite difference, and so on. But these are merely the names of numerical techniques to solve the nasty differential equations. Mathematically, they rely on a common base, the continuum description of material, which is mathematically scale invariant. And second, thermodynamic modeling is a technique which can predict the equilibrium phase compositions of reacting chemical systems based on experimental databases. Thermodynamic modeling techniques have been used by industry and academic community with great success in cement. In Transcend, project number 14 built an experimental database for the interaction between cement hydrates and water vapor. It is covered by its own videos, which can be found on the Nanocem homepage. We now review 4 short case studies how to use molecular dynamics, Monte Carlo and Lattice-Boltzmann in cement science. These are examples taken from Transcend projects. Before we close this, why do scientists use models? Particularly when it comes to numerical modeling in cement, this is a question which is often raised. Rarely, numerical modeling can replace experiments. So one may ask, so what? However, modeling is something much more fundamental. Stepping back, one may realize that many of the words scientists use in their day-to-day work actually refer to models. For example, what is an atom? Is it a small ball with some bonds as we often imagine? Quantum mechanicists say that's wrong, but for many chemistry purposes that's already quite a powerful concept. Thus we say, a model is a concept to interpret an observation. An ideal model has 3 properties. First, it makes sense, so we can grasp it. And the easier it is, the better. This is sometimes also called Occam's razor. Ideally, it is consistent not just with one observation, but with results from different techniques. And finally, an ideal model has a predictive capability. If it's qualitatively, it's good. However, quantitatively is better, particularly for industry purposes. Looking at the models used in cement science, not all models fulfill all of these criteria. Often, experimental data is fitted with empirical models, polynomials or other functional forms with many parameters. Such models can be quantitatively predictive over the data range they cover, but they don't make sense beyond the rule, with enough parameters one can easily fit an elephant. We would like to conclude with some remarks about the process of making a model. Making a model means to reduce the complexity of reality to some degree so that human beings can comprehend it, either by using merely their brains or with the help of a computer. This is probably the key step in making a model, and maybe also the biggest problem in the communication between modelists and experimentalists. Molecular dynamics. The idea of molecular dynamics is refreshingly simple. Remember the ideal gas from your time at university. The gas atoms are idealized as hard spheres which race through space. Occasionally, the atoms collide as shown in the animation. This animation is in principle a super simplified molecular dynamics simulation. In reality, the fluid molecules are a bit sticky. If we lower the temperature, the gas molecules become slower. Now, they do not have enough energy to fly away from each other, so clusters of more than one molecule form and eventually all molecules sit in the same cluster. Molecular dynamics consists of two parts. First, software, which tracks merely the position of each atom and its velocity. And second, a description of the interactions between the atoms. Obtaining this interaction is not straightforward. It may require quantum mechanics methods such as the aforementioned DFT. The description of the interatomic interactions, however, is everything but complicated. It is described by giving a function which describes the force acting along the center-to-center direction of the atoms as a function of distance. It is therefore called a force field. If the atoms are far away from each other, like this, the energy is zero. If they come closer, they start feeling the presence of each other. In the example, the positive force indicates a long-range attractive interaction. However, when the atoms come very close, the force quickly reaches very large negative values, which are repulsion. In the example, we have shown the most important model force field, which is often called the Lennard-Jones potential. Potential? Well, note that in the literature, particularly physicists usually talk about interatomic potentials instead of force fields. This is because physicists like potentials. They prefer the concept towards the force field. However, the meaning is the same. The spatial derivative of the potential energy is a force. Returning to our example, this curve explains how the particles become sticky. If two particles collide with a lot of momentum, the momentum will be big enough to overcome the attractive interaction. This is equivalent to high temperature. If the temperature is lower, the atoms have less energy and the particles cannot leave the potential well as shown. These are the essentials of MD. It is important to note that the principle is extremely simple. The practice, however, is not. Developing an efficient MD simulation is an art for itself, therefore it is recommended to use software which, at least for academic users, is available free of charge. So what can molecular dynamics do? MD can look at the dynamics of processes in liquids on atomic length scales, such as diffusion, dissolution, and so on. It can also look on the structures formed by the atoms in particular situations. Generally, MD is a powerful tool, but it is not the silver bullet it is sometimes advertised as. It requires good information about the potentials, which may not be easy to lay hand on. In cement, this is a problem. Also, it is computationally expensive, as our case study from a Transcend project illustrates. Let's look at the first case study of this video. MD was used to calculate NMR relaxation times from MD. For the basic ideas behind NMR, please consult other videos on the Nanocem homepage. For this video, it is sufficient to know that the NMR relaxation time of water depends on its mobility, to be exact, on the cross-correlation function of the water molecules. That's a statistical measure which we don't want to discuss in detail. The former notion is sufficient. In bulk water, the water can move freely and is highly mobile. Simulations were carried out in a cement pore, which was water confined in tobermory-like CSH. A simulation snapshot can be visualized like this. It was found that water absorbs in approximately 2 diffuse layers on the surface, and that water actually diffuses within these layers on the surface. Whilst there is exchange between the surface and the bulk water in the pore, the average mobility of the water molecules is considerably decreased. This data could have been used as input for NMR theory. Well, if MD were not too slow. The simulation of 1 nanoliter of water for 1 nanosecond takes approximately a week. In comparison, NMR relaxation times are in the order of microseconds. Thus, mobility data is required over such a long time interval, and Serge-Henri Akashia, the PhD student working on this, would never finish. This problem was overcome by combining molecular dynamics with another technique, Monte Carlo simulations. Monte Carlo techniques are an extremely wide field. Their common principle is to approximate reality in a suitable stochastic model. This will be illustrated by 2 examples. The first one is a standard introductory example from MC textbooks, Monte Carlo integration. The relative area of the circle to the remaining areas of the square can be determined by randomly choosing points within the square and test whether they are in the circle or not. This can be done by a computer, actually even in reality by dropping peas on a piece of cardboard. By taking the ratio between the points in the circle and those outside, one can obtain the relative area, and in this particular example, the number pi. A few general comments about MC techniques. In principle, MC can be applied to everything as long as a suitable stochastic model can be found. In cement science, MC techniques have been used to learn about the growth of structures, their dissolution, water dynamics, and interactions between cement particles. However, often, as in the MC example discussed next, this requires input from other techniques. Let's return now to the problem from the previous slide. We have already learned that molecular dynamics can simulate the behavior of water in a pore, but only for a few nanoseconds. We need the cross-correlation of the water molecules, a descriptor for their mobility, over the range of microseconds. This means that the simulation needs to run as long. One way to do this is to use a kinetic Monte Carlo scheme to describe the movement of water in the long time limit. What does this mean? Well, let's have a look. We discretize now the domain as a grid. At the domain boundaries, we place walls which represent the CSH. We have seen previously from the MD simulations that water can be, first, in the bulk of the pore, which is shown in white. It can be also adsorbed on the surface, which is shown in red, or in a low mobility surface layer, shown in yellow. The water molecules are mobile. Molecular dynamics identifies different diffusion coefficients of water. A surface diffusion coefficient, which is 2-dimensional, a slow diffusion coefficient in the low mobility layer, and a diffusion coefficient in the bulk water. This can now be translated to rates, how often a water molecule jumps on the lattice. This leads to the computation of further rates. It was demonstrated that for short times, this model produces the same mobility data, or the cross-correlation function, as the molecular dynamics simulation. Running this Monte Carlo model is much faster than an MD simulation. Just consider no small time steps for the integration of the equations of motion, no expensive evaluation of the potential functions. That's why this work, which was carried out by Nick Howlett in a Transcend partner project, extended the timescale of the molecular dynamics simulations towards microseconds, so that the data could be used for NMR calculations. We would like to conclude that Monte Carlo comes in a plethora of different flavors. Therefore, we will point out 2 other examples from cement science which you have likely heard about: the numerical sheet growth model and Mike. The numerical sheet growth model describes the growth of 2-dimensional sheets in 3-dimensional model pores to model CSH growth and the resultant structure. The underlying kinetic model uses an event-driven process similar to the Monte Carlo model for water dynamics in the nanopores, which we have just seen. A link can be found below this video on the Nanocem webpage, which shows a video about the sheet growth model. Mike is a model simulating the growth of hydrates within the capillary pore space of cement paste. It uses a random sequential addition algorithm to place the cement particles in the simulation box. ASA is the simplest model of particle packing. However, note that the actual evolution of the structure in the model is totally deterministic. A link to the Mike homepage is also provided below this video on the Nanocem webpage. Continuous modeling techniques. Many of you might have never heard about continuum modeling. This is because people often refer to it as finite element, finite difference, finite volume, lattice-Boltzmann techniques. However, note, these are merely mathematical solving techniques for the equations of the same underlying model ID. We look first at the principle of this technique. Let's try to understand what it means to say that matter can be seen as a continuum. We all know that material is made of atoms, as illustrated here. In the continuum picture, material is seen as a continuum, which means that at any point, at any time, we can define variables such as density, velocity, or stress. Compare this with an atomistic view. We cannot define, for example, a meaningful velocity at a point without an atom, since it is independent of the actual state of the material. Continuous models are built by combining two ingredients: fundamental physics properties, like conservation of mass, momentum, or energy at any point, and so-called constitutive equations, which link the conserved variables. We exemplify this by the convection diffusion equation. The constitutive equation, which is often empirical, is in this case Fick's law. If one combines it with mass conservation, one obtains the convection diffusion equation. The methods mentioned above, finite element, finite difference, merely solve the relevant equations within the relevant geometry, such as the convection diffusion equation for mass transport or the Navier-Stokes equation for bulk fluid flow. Often, the problem to solve the relevant equation is much harder than actually deriving them. It is important to note that these equations are inherently scale invariant. They always hold as long as the fundamental assumption, which is a continuum description of the solid, is valid. Each of these solvers has different strengths and weaknesses, particularly when it comes to dealing with complex geometries. Simulation of transport processes in cement paste faces highly irrelevant geometries. That is why the last case study of this video focuses on a technique particularly suited for this: Lattice-Boltzmann. Lattice-Boltzmann is a solver for the Navier-Stokes equation and some differential equations of similar form. Lattice-Boltzmann is different from the other solvers in so far that it does not solve the equation directly but does something else. Lattice-Boltzmann simulates a gas on a lattice. Gas molecules can sit at each node of the lattice. At each time step, the fraction of gas which moves to the left, to the right, up, down, and diagonally is known. During each time step, two things happen. A simplified collision model alters the distribution of gas molecules between the different directions, and afterwards, the gas molecules move to the next node in their direction, like this. This is the whole principle behind Lattice-Boltzmann. The actual equations behind this are also amazingly simple. It can be shown that the behavior of the lattice gas approaches the behavior of the Navier-Stokes equation in the incompressible limit. This is fascinating on its own right, but for cement that is great for a number of reasons. The complex geometries in cement can simply be mapped on a lattice, and by defining an appropriate local behavior for each node, the geometry can be adopted. In the example here, the solid-fluid boundary can be described by placing bulk fluid nodes on the left and solid nodes on the right. Thus, flow in a complex cement structure is no problem, and the algorithm is very, very simple. It comes at a cost, of course. It is expensive to run and may require a supercomputer for large domains and more complex simulations. Today, however, supercomputer time is cheaper than human time, and first packages for Lattice-Boltzmann are available, which perform the expensive computations efficiently on supercomputers. Thus, it is a promising approach for cement science. I'd like to close this introduction to LB with two warnings. First, Lattice-Boltzmann looks similar to a molecular simulation, but it is not. It is a continuum method which always converges to the continuum result. And second, if one reads the Lattice-Boltzmann literature, it often appears like a big toolbox where one can draw different techniques to handle bulk fluid, solids, and so on. However, not all these tools work together, so one has to be careful when one plans a simulation. Lattice-Boltzmann case study. In Transcend, Lattice-Boltzmann was used to understand the widespread of literature permeability data of cement paste. The model was based on cement structures generated by Mike. The following regions were identified: unreacted cement in gray, CSH in black, crystalline solids in green, water-filled capillary pore space in blue, and air-filled capillary pore space in white. Two situations were studied. First, water flows through such a structure. The following assumptions were made: unhydrated cement is impermeable to water, crystalline solids are impermeable, and air-filled capillary pores were also considered impermeable to water. In the water-filled parts of the porosity, bulk water movement was enabled in the water-filled regions, and the CSH was assigned a permeability of 7 × 10⁻23 meters squared following a paper of Powers. In the second situation, the flow of air in cement was studied. Permeability measurements using air are common in the literature. Now, the properties of the different phases are partly reversed. The unreacted cement and the crystalline solids are still considered impermeable, but the water-filled capillary pore space is considered impermeable to gas, and the bulk fluid behavior is assumed in the air-filled capillary pore space. Also in this case, the CSH, whose pores are assumed to be still filled with water, was considered impermeable. The result is plotted as water-filled fraction of the capillary pores of the total sample volume against the permeability. The curves for water look like this, for air like this. It was demonstrated that a variety of previously published literature data could be placed on this curve if the sample conditioning, or in other words, the degree of filling of the capillary pore space, was taken into account. This work was just carried out for a single-phase fluid, like water or pure air. Current work, which has already been begun by Mo Zalzaleh and Peter MacDonald, extends these ideas towards multiphase fluids, which would enable the simulation of sorption isotherms in the cement paste. In this video, we have reviewed some of the modeling techniques used in Transcend. We have seen how techniques have to be split into continuum and atomistic techniques, and which techniques can be used at different length scales. We have also seen how different techniques can be combined to overcome individual techniques' weaknesses, as in the case of MD and MC. We have also seen the possibilities Lattice-Boltzmann offers to simulate transport in cement. Let's close this video with some general remark about modeling. The purpose of all modeling is to understand the observations made in experiments. One can never see modeling disconnected from the experiment.